Okay, and finally, where we left off was we were about to go over atomic solids. This would be the last category of the types of solids we need to go over. You've got non-bonding and you've got metallic solids. And also network covalent solids. So non-bonding solids, for example, though basically this category is limited to the solid versions of the noble gases. So xenon, especially because that one's relatively easy to freeze compared to the others, but solid helium and argon and neon also. These have dispersion forces only. And because of that, they have very low melting points. The melting points, though, increase with mass. And so xenon, being the heaviest of the noble gases, is the one that's easiest to turn into a solid, but the others can be as well under fairly extreme conditions. We've also got metallic atomic solids, and we've seen lots of examples of those when we talked about metals. And so examples of metallic solids would be metals, duh. And so basically, any metal, whatever it is, chromium, iron, aluminum, gold, tin, things like that, they're all metallic solids. They have metallic bonds. And so what you essentially have are fixed metal cations that consist of the nuclei and the core electrons of the metal atoms, surrounded by what's often referred to as a sea of mobile valence electrons. And because of the, this is the reason that metals conduct electricity. Is because of those mobile valence electrons. And also metals tend to be quite tough, and the atoms are fairly strongly attracted or attached to one another because they're essentially fixed in place, and they have this sea of valence electrons that they all share together, and that helps lower their energy. Metallic bonds are not directional, which means one atom can be close, or can be basically attracted to several others in every direction. Okay, so it's not just any one given metal atom can be attracted to other metal atoms all the way around it in every direction. And because of this, they tend to form close packed crystal structures. Although different metals form different types of crystal structure. Nickel is cubic close packed, and zinc is hexagonal close packed. The strength of the metallic bonds varies. can vary quite a bit. And that's why the melting points vary quite a bit also. And, I mentioned cesium, which has such a low melting point that the heat from your hand would be enough to melt it. Also, I didn't, for some reason, didn't even think of mercury, whose melting point is below room temperature. Mercury being a liquid at room temperature. And iron, on the other hand, has a melting point of 1800 degrees Celsius. And iron is not the highest melting metal, not by any means. There are others like tungsten and osmium and iridium that have much higher melting points than that even. And so that's a pretty wide range of melting points for metals. And the last group under basically the last group under atomic solids would be the network covalent solids. These are atomic solids that form networks. And one is diamond, and one is one example of a network covalent solid. Another is graphite. Both of these are made up of carbon atoms. The diamond is carbon atoms that are bonded together in a three-dimensional network. Graphite has carbon atoms bonded together in two-dimensional networks, and they basically form flat sheets. And also there's silicon dioxide. The difference is, of course, diamond and graphite both being carbon, those are elements, whereas silicon dioxide is a compound. Only it forms the same type of network covalent solid that carbon does when it's in the form of diamond. And so essentially in silicon dioxide, you have a whole bunch of silicon atoms and a whole bunch of oxygen atoms that are all bonded to each other. And the ratio just works out to 1 silicon for every 2 oxygens. But it is a three-dimensional network, much like diamond. These networks involve covalent bonds, which of course are directional. And because of that, an atom can't just be attracted to a bunch of other atoms in all different directions. And so one of the consequences of that is that network covalent solids do not form close packed structures. But they do have very high melting points. And in fact, carbon, whether in the form of diamond or graphite, and silicon dioxide have, among the highest melting points known for anything. The diamond form has each carbon and each carbon is bonded to other carbons in a tetrahedral arrangement. And what that leads to is a three-dimensional network of carbons. So you've got a carbon in the center. And this is our sort of crude way of drawing a tetrahedron on a piece of paper. And there are carbons at each of these positions too. And each of those is bonded tetrahedrally to other carbons as well. because the electrons are confined to sigma bonds between carbons, diamond does not conduct electricity. Just like most other tetrahedrally bonded compounds don't conduct electricity. Methane, CH4, carbon with hydrogens in each of the outer positions, that doesn't conduct electricity either, because the electrons are localized within each of these bonds, which is a very confined space. They can't move around easily. On the other hand, with graphite, you have a different arrangement. Carbons are bonded to other carbons in flat sheets. They form six-sided structures similar to benzene. And these six-sided rings are bonded to each other in a two-dimensional network. And actually, the electrons are delocalized because the structure of graphite involves both sigma and pi bonds. So the electrons are delocalized over these sigma and pi bonds across the entire sheet. And because of that, graphite does conduct electricity. In fact, a graphite pencil will conduct electricity. It's one of the first things they tell you if you go to school to be an electrician is never hold a pencil in your hand while working around live electrical lines, because that's a good way to get zapped. So graphite does conduct electricity. The structure, if you look at it from the top, the carbon rings look something like that, and they fit together tightly, kind of like this, allowing for my feeble ability to draw them. But you can kind of see how it's almost like a flat honeycomb kind of structure. And they go on and on in two dimensions. So you have sigma and pi bonds between the carbons within the sheet. So they're held together pretty strongly. But between the sheets of graphite, you only have dispersion forces. And so the sheets slide easily over one another. And so graphite is a good lubricant. They have the graphite lubricant that you can buy for, particularly for locks. That's the best kind of lubricant for like the locks on your car to keep them working through the winter. You can spray a little bit of this graphite lubricant in it. It's basically like WD-40, except it's black because it's got graphite in it. So it's kind of nasty stuff, but it works really well. Also, pencil lead is a good lubricant too. If you have something like a hinge that squeaks, or something that you want to move more easily, you can, and you don't have any oil or any WD-40 around, you can just basically rub some pencil lead on it, and that will often take care of it, because that's a good lubricant too. And the last category is the silicates. These are compounds of silicon and oxygen, like silicon dioxide. They're very common because, for one thing, silicon dioxide is the principal constituent of sand. And there's sand all over the place on Earth, under the oceans, on beaches, in deserts, and also a large percentage of dirt in most places is made up of silicate type compounds as well. Silicon, the element, is actually the most common element on Earth because it's all over the place in dirt and sand and things like that. Quartz, which is the crystalline form of silicon dioxide, is an array of SiO4 arranged in tetrahedrons. SiO4 would have silicon in the center and oxygens around the outside, but then these oxygens are bonded to other silicons, and those silicons are bonded to other oxygens, and so on. So the oxygens are shared with other silicons, and so on and so on and so on. The amorphous or non-crystalline form of silicon dioxide is better known as glass. So when you have a bunch of SiO2 molecules that are thrown in together kind of every which way, what you get is glass. Quartz, okay, so quartz is arranged like that. The silicon-oxygen bond is very strong. And so silicates tend to have very high melting points. And well, as I mentioned a moment ago, glass is also silicon dioxide, but it's amorphous. Okay, so that's, and I mentioned the other day that one of the things that makes glass so weird and so difficult to predict what it's going to do, and so difficult to work with, is the fact that it's amorphous. Crystalline compounds tend to be fairly predictable in their behavior. It's relatively easy, once you've gone through the training and you know what you're doing, it's relatively easy to cut diamond, because all you have to do is find out where the spaces between the sheets of carbon atoms are, and if you hit the diamond in that spot, it'll break nice and cleanly along those lines, and you'll have a nice, smooth, flat surface. It's not easy to work with glass. If you try to cut glass for, like a window or something like that, it's really pretty difficult to do that, and it takes a lot of training, actually even more training than it does for cutting diamonds. The advantage is glass is a lot cheaper than diamonds. And it's unpredictable because there are no planes of atoms in glass for you to, try to cut between. You're kind of taking your chances, and if you choose the wrong place to try to cut it, the crack is going to go off in a different direction, and you're going to ruin the piece of glass, and you'll have to try it again. And that's, again, due to the unpredictable arrangement of the molecules in glass versus something like diamond. That brings us to the end of this chapter. That's the end of chapter 11. And that's probably also the end of lectures for this course. I know that the schedule included some stuff from chapter 12. That was extremely optimistic. We do have some extra time, but I don't believe we have enough time to finish chapter 12, so I don't see much point in starting it if we can't finish it. Actually, at the beginning of the semester, if you'd asked me, I would have predicted that we probably wouldn't even have gotten to chapter 11. So we've actually done better than I really expected to. And so keep an eye out for more lectures, but like I said, this will probably be the last one. It's certainly the last one for this week, and we've only got one more day next week anyway. So, so basically you can use the extra time to start reviewing for the third exam and the quizzes. And there'll be more information, or the last quiz rather. There'll be more information coming on that soon. So you can keep an eye on Blackboard for that. And so until then, I'll see you later.